Once you know about orbitals, you have a couple of questions that you can ask. And at least two of those are, what orbitals are going to have electrons in them at any given time? And how many electrons can actually fit within a single orbital? And up until now, we've considered things like mass or charge when talking about properties for electrons. But now we're going to add another property, and that property is electronic spin. And electrons behave as though they are spinning spherical charges. So they behave like they can spin in one direction or they can spin in the opposite direction. They're not really spinning spherical charges, but they behave as though they are, and this becomes a good way to discuss the property. So in general, spinning charges are going to produce a magnetic field. So if you spin a charge one way, your magnetic field is going to face in a certain direction. So we'll call it north. And if you spin your charge in the other direction, the magnetic field is going to face in the opposite direction. And there's only two possible directions of spin. You can spin one way or the other. Spin, like lots of different things, is quantized. And that means you produce a magnetic field that goes in one direction or the other. And this property, this electronic spin, is associated with another quantum number. Right? So now we've seen principal quantum number n, we've seen the quantum numbers L and ML, and now we're going to add a fourth quantum number, ms. And this quantum number, unlike the other three, only applies to the electron itself, not to the orbitals. And as I mentioned earlier, it can only have two possible values, spinning in one direction or spinning in the other. And there are three different ways that we typically will represent these. So we say that you have either spin plus or minus a half. So spinning in one direction or spinning in the opposite direction. Sometimes we'll call those spin up or spin down. And sometimes we'll represent it with an arrow. And the arrows we use to represent single electrons typically don't have a full arrowhead, they only have half of the arrowhead. So alongside this spin property, electrons are going to follow a rule called the Pauli exclusion principle. So the Pauli exclusion principle tells you that no two electrons can have an identical set of quantum numbers. So any two electrons cannot have all four of these quantum numbers the same. Three of them can be the same, but at least one of them has to be different. And the Pauli exclusion principle confirms that there's a maximum of two electrons that can reside in any single orbital. So we're going to look at an example to work this out. So if we look at the 1s orbital, we can work out three of the quantum numbers. N equals 1, L equals 0, and ML equals 0. So now imagine that you put an electron into that orbital. That electron is going to be associated with N equals 1, L equals 0, and ML equals 0. And there are only two possibilities for the spin quantum number, ms. So these are the sets of quantum numbers that you could get for electrons that exist inside the 1s orbital. So you could have N equals 1, L equals 0, ML equals 0, and then ms is equal either plus 1/2 or minus 1/2. There are only two possibilities. So if you tried to add a third electron in, you'd get this situation. And as soon as you get here, you realize that if you have a plus 1/2 electron, then you'd be duplicating the very first one. And if you had a spin minus 1/2 electron, you'd be duplicating the second one. So there's no way you can add a third electron to any given orbital. And this is true for any orbital, the 1s, the 2p, the 4f, it doesn't matter. Any orbital, any single orbital can only have a maximum of 2 electrons. So if you look at the 3p subshell, if we look at one of the specific orbitals within that subshell, we can work out how many electrons can fit inside the 3px orbital. And the same kind of process as we followed for the 1s orbital applies here too. So we know the n equals 3, we know L equals 1, and the x, y, and z p orbitals correspond to an ml value of -1, 0, or +1. It doesn't really matter. They're all effectively energetically equivalent, so we can just pick one. And then we have a spin of plus or minus a half. And again, there's only 2 electrons that can fit before you start duplicating sets of quantum numbers. Now, the nice thing is, if you look at the y and z orbitals, each of those can also hold 2 electrons, which means that the entire p subshell can hold a total of 6. And by a similar kind of process, you can work out that the d subshells can hold a total of 10 electrons, each individual orbital holding 2.